In this video, we are going to discuss the properties of gases, and there's 5 important properties that we're going to discuss. Number 1, gases have variable shape and volume. Number 2, gases compress uniformly, and then they also expand uniformly. Gases have a very low density, and if we mix multiple gases together, they will mix uniformly. So we're going to take a look at these one by one. So first up, gases have variable shape and volume. So we talked earlier in the class how the difference between solids, liquids, and gases. One difference is solids, for example, have a fixed volume and a fixed shape, and liquids have a fixed volume but a variable shape. Well, gases have variable shape and variable volume, so that means if you were to put a gas in a container that's shaped like a balloon, then the gas has the shape of that balloon. And if you were to put the gas in the shape of like a cylinder, it's going to have the shape of that cylinder. Number 2, gases compress uniformly. So a common example would be like the cylinders in your car engine. We can compress this gas so it's actually got a piston on there, and we've got gas particles in here because it's going to combust, and we can press down on it. So the compressing uniformly part of it means that when we compress down, all of those gas particles will get closer together at an even rate. So we're not going to have the gas particles like all bunching up at the corner of the container at the bottom or something like that. And actually, if we reduce the volume enough, we could cause the gas to liquefy. So it could transition from gas to liquid. Number 3, gases expand uniformly. So same kind of thing, if we allow a gas to expand in the container, so we could use our piston in a vehicle example again. So we got the piston down below, and then we draw the piston up so that this space here where the gas is, that gets larger. The gas particles are going to fill that space evenly. They're going to go to all spaces inside the new volume. So it might be like this, where we expand the piston and now there's gas particles everywhere inside there, and they're everywhere inside that thing, all corners, all spaces. There's no vacuum in there. Number 4, gases have a low density. So the density of air is about 0.001 grams per milliliter, and we've got it in units of grams per milliliter because that's a common unit of density for liquids. And just to compare, so water is 1.0 grams per milliliter, so you see that this is a very, very small number compared to the density for water. And usually for gases, actually, we'll provide the density in units of grams per liter just because they're so dense. The density values are so small, we'll change the units. But what this really means, so everyone's observed, if you have a cup of soda in like Coca-Cola or Dr. Pepper or something, the bubbles float into the top. So the bubbles float to the top because gases are less dense than water, less dense than liquids. So number 5, gases mix uniformly with other gases in the same container. So if you have 2 different gases and you put them in a container, so I'll do open circles and dark circles, they will be spread out evenly throughout the container, just kind of like a homogeneous mixture. That's what we mean by that. Two gases, it could be like argon and helium, and they're going to spread out evenly like a nice, beautiful, homogeneous mixture. And then we have mixtures of gases all over the place. So like air is a mixture of gases. We've got CO2 and nitrogen and argon and oxygen and probably some nitrogen monoxides in there, but it's a mixture of gases. And when automobiles emit nitrogen oxide gases in the atmosphere, they mix with other atmospheric gases. So we could also have dinitrogen monoxide and nitrogen monoxide, but we've got a mixture in air. And then if we've got a mixture of gases in a sealed container, it'll of course be a homogeneous mixture. So there's no way for you to see the individual gas particles, to see the nitrogens from the argons. It's kind of like a solution of gases. All right, gas pressure is the result of constantly moving gaseous molecules striking the inside surface of their container. So that is how we are defining pressure, is the molecules hitting the inside. The more often the molecules collide with the sides of the container, then the higher the pressure. So if these little purple spheres are bouncing around on the inside and they're hitting the walls more often, then we're going to measure a higher pressure on our little pressure gauge. And then the higher the temperature, the faster the gas molecules move. So they're going to be hitting the sides of that container more often, but they're also going to be hitting with more force. And both of those are reasons why we might register a higher pressure when we increase the temperature. And then obviously, if we were to lower the temperature, we'd get a lower pressure because the particles are just not hitting the sides as often. They're not hitting with as much force. It's kind of like the difference between just tossing a penny at the wall versus really trying to throw that penny at the wall as fast as you can. If it hits it with more pressure, it's going to, or rather, if the penny hits the wall with more force, it's applying more pressure when it does hit the wall. Same kind of idea with gas particles. Now, atmospheric pressure, same kind of idea, but it's a result of the air molecules in our environment. So the air, just the atmosphere on planet Earth, whatever you're feeling at the moment on your skin, and you don't feel it because you're used to it, but that's what we will call atmospheric pressure. And Evangelista Torricelli invented what's called the barometer. So we have an example of a barometer over here, but it's a way to measure atmospheric pressure. And this is standard atmospheric pressure at sea level, so 760 torr. Another unit is 29.9 inches of mercury. So we would abbreviate that, inches of mercury. Torr is just abbreviated to Torr, but that torr came from his last name, Torricelli. But how a barometer works. So the atmospheric pressure is pushing down on the outside. So we've kind of got this dish that's open to the air, and then we've got mercury inside the dish, and the atmospheric pressure can push down on that surface. So it's applying a pressure. And then that forces the mercury up inside the tube. And then if the pressure is greater on the outside, then this level is going to rise up higher on the inside. And then that height difference, so they've got the height difference right there in inches of mercury and also torr. This should say torr right here. But that's how you measure the atmospheric pressure, by looking at the difference in height. So how high this rose inside the tube versus where it is down here in the dish. Standard pressure is atmospheric pressure at sea level. So we have it in different units down here, 29.9 inches of mercury. 1 atmosphere is a very common unit we'll see in the laboratory. 760 torr is also very common. But these are just some common units. PSI is one that you'll see commonly with tire pressure. So if you look at the inside label of your vehicle, usually like on the driver's side door, it'll tell you to what pressure you should inflate your tires. And I think in my vehicle, it's like 33 or 34 PSI. But that's another common unit you'll see. Kilopascal's not so common in everyday American culture, but millimeters of mercury and inches of mercury, I think we might see in weather reports. But I think most commonly for our calculations, we might see ATM, atmospheres. So here's an example of just converting between pressure units. So the problem says the barometric pressure is measured to be 26.2 inches of mercury. What's the pressure in the new units of atmosphere? So we're just converting units. So we want to calculate atmospheres, and we were given inches of mercury, and then we have this conversion from the previous slide. So setting up our 26.2 inches of mercury, and then this conversion, we're always going to put the units on the bottom that we want to cancel out. So canceling inches of mercury, and 29.9 inches equals 1 atmosphere, and so that's how we get the 0.876, and our units are now atmospheres. So I think one thing that's very important conceptually is understanding which variables affect gas pressure. And there's 3 other variables that can affect pressure that we'll go over. So number 1 is the volume of the container that is holding that gas. Number 2, the temperature of the gas. And number 3, the number of molecules, or basically the number of moles of gas that are in that container. And there's a bunch of different gas laws that relate these to pressure, and then there's also something called the ideal gas law that relates all of these. But we're going to go over those in due time. So first up, with volume versus pressure. So when volume decreases, the gas molecules are going to be colliding with the containers more often. So you imagine, I'll draw two of my pistons like that are in the car. So here's my cylinder, and then I depress it down here so I have a smaller volume. So you've got some gas particles here in the cylinder, and they're all bouncing around. And then you compress the cylinder, and now they're going to be buzzing around much faster. They're hitting the walls more often because now they're in a smaller space. You imagine how long does it take to go to the bottom and then bounce back up to the top, and then over here, just bouncing around. It's going to hit the sides more often in the smaller space. So the idea is that when the volume decreases, the pressure is going to go up. And then the converse is true. If the volume increases, the gas molecules are going to be colliding with the walls of the container less often, so the pressure goes down. So if the volume goes up, pressure goes down. And then one thing that's important with this relationship we just talked about is we are assuming that temperature and the moles, so lowercase n, stands for moles of gas. We're assuming that the temperature of the gas and the amount of gas that's in that container is remaining constant. But if the volume decreases, then the pressure increases, and if the volume increases, pressure decreases. So we say that they are inversely proportional. If one goes up, the other goes down, and vice versa. They're inversely proportional. Next up, temperature versus pressure. So when the temperature decreases, the gas molecules are going to be moving slower, and they're going to be colliding with the walls of the container less often. So the pressure that we measure is going to go down. So as the temperature goes down, the pressure also goes down. And when temperature increases, the gas molecules move faster. So they're going to collide with the walls of the container more often. So the pressure goes up. So as the temperature goes up, the pressure goes up. And similar to the last slide, we're making an assumption that the volume of the container and N, the moles of gas, are remaining constant. So V is volume, and again, N is basically how much gas you have, but more specifically, it's the moles of gas. For this temperature-pressure relationship, we're assuming that V and N are remaining constant. As the temperature goes down, the pressure is also going to go down, and as the temperature goes up, the pressure goes up. So next one, the number of molecules versus pressure. So this is basically our letter N. N stands for moles. It's kind of like, it's really more like N is for number of molecules, but in chemistry, we use the lowercase letter n to represent moles, but the amount of gas you have versus pressure. So if the number of molecules inside the container goes down, that means there are fewer gas molecules colliding with the walls of the container. So the pressure is going to go down. So as N goes down, pressure goes down. And when the number of molecules goes up, now there's more gas molecules bouncing around in there. So they're going to collide with the sides of the container more often. So pressure is going to go up. So as moles of gas goes up, the pressure goes up. So in this example, notice we've got an extra little thing on here. So that's kind of like a gas cylinder. And what we're doing is we're injecting or removing some gas. So here's like our initial one, and we say molecules decrease. So it's like we leaked some gas out of the container, and you see there's fewer little purple circles in their drawing. So as the number of molecules goes down, the pressure also goes down. And if we were to inject more gas molecules in the container, so we like open this little valve here and let more gas in from the pressurized container, as molecules increases, pressure increases. So notice we've got more purple spheres over there. And again, we're assuming that the other variables, temperature and volume, are remaining constant. Temperature and volume remaining constant. Now these last two that we just discussed, so going back a slide, temperature versus pressure, and then this slide where it's moles of gas versus pressure, since they change the same way, like if one goes down, the other goes down, and if one goes up, the other goes up, we say they're directly proportional. So next, Boyle's law. So essentially, the names of these gas laws that describe all these relationships that we just talked about. So first up, Boyle's law states that the volume of a gas is inversely proportional to the pressure, and assuming constant temperature and also the sample of gas is not changing. So inversely proportional, like we saw, means that two variables have what's called a reciprocal relationship, meaning if the volume goes up, the pressure goes down, or if the volume goes down, the pressure goes up. And mathematically, you might represent it this way. So this little symbol here means that it's proportional to. So the volume is proportional to inverse of pressure. So if the volume goes up, then the pressure is going to go down. And just if you think about mathematically, if you've got a number in a denominator, so I'll say 1 over x, the rule is if the denominator gets smaller, then that fraction is actually getting bigger. So think of like 1/4 versus 1/3. So 3 is smaller than 4, but 1/3 is a bigger piece of the pie than 1/4. So that's kind of how you can help remember those two. Now, graphically, Boyle's law looks like this. So we've got volume on our x-axis and pressure on our y-axis. So at low volumes, so over on this region of the graph, low volumes, we get high pressures. And then when the volume increases a lot, then the pressure decreases. So inversely proportional, an inverse relationship. So a little bit more about Boyle's law. If we introduce an arbitrary proportionality constant, and we'll use the letter K, we can write Boyle's law as follows. So notice now we're using an equal sign instead of that proportional to sign. So volume is equal to some arbitrary number K times 1 over P. And we could rearrange that so we don't have any fractions. We'll say PV equals K. And then this is just an arbitrary number, but we could talk about two different situations. So like P1 and V1 in like a trial one or before we made a change. And then we could talk about P2 and V2 as in the pressure and the volume after we made some sort of change or in another trial. And since the pressure and volume for a specific sample of gas at a temperature must always equal this K, we can equal these to each other. So Boyle's law is P1 V1 equals P2 V2. So the pressure times the volume before we made some sort of change equals the pressure times the volume after that change. So here's an example, but essentially, since we've got this P1 V1 equals P2 V2, if you know 3 of the variables, you can solve for the 4th one, and it can be any of them. The problem could give you, the initial volume and the final volume and the final pressure, and you have to solve for the initial pressure. But we can rearrange Boyle's law to solve for any of these variables. So, for example, this would be the type of problem where they're asking for the new volume, and they give you the pressure before and after, and they also give you the initial volume. This type of setup would be if they're asking you for the new pressure, they give you the volumes before and after, and they give you the pressure beforehand. So let's do this where we actually solve a real problem. So it says a 3.5 liter sample of methane gas exerts a pressure of 1,550 millimeters of mercury. What is the final pressure if the volume changes to 7.00 liters? So the challenge with these types of problems is just identifying what's P1, what's V1, what's V2, what am I solving for? So since this says what is the final pressure, I'm going to go ahead and call that P2. And then I notice I've got 2 volumes. I've got 7 liters and 3.5 liters. So those are my V's. And I just have to think about which one is V1 and which one's V2. So it says if the volume changes to 7.00 liters. So just kind of reading the language and interpreting it, that tells me that's equal to V2, which means the 3.5 must be V1. So then the only variable left is the P1. That must be the 1,550 millimeters of mercury. So that's my P1. So that's why they've plugged in 1,550 millimeters of mercury for P1. And then we said that V1 was the 3.5 and V2 was the 7. So they've arranged it as 3.5 divided by 7. the liters cancel out, and we should get 775. And then the units, it's whatever units we had initially for P1. So that's why they have the units here as millimeters of mercury. Now, one thing that's really helpful is just think about conceptually what was supposed to happen. So the volume changed from 3.5 to 7. So the volume went up. Now, because of the inverse relationship, we expect the pressure to go down. We calculated the pressure change from 1550 to 775, so that is consistent. That's good. We indeed calculated a lower pressure. So that's why it says the volume increased and the pressure decreased as we expected. It's just kind of like a way to check your work. Okay, next one, Charles's law. So Charles's law is basically about how the volume is directly proportional to the temperature in Kelvin. So here's our proportional symbol again. The volume is proportional to the temperature, and we're assuming constant pressure this time. And we're also assuming the sample of the gas, like the number of moles, number of gas particles, is also constant. So notice that we get a straight line this time. So as the temperature goes up, the volume also goes up. So just a nice simple straight line. So similar to what we did for Boyle's law, if we introduce an arbitrary proportionality constant, the letter K, we could write Charles's law either like this or like this, where we've got volume is equal to that constant times temperature, or we could divide temperature on both sides of the equation to get this. And then we can do something similar. So like the initial volume and the initial temperature, if that's equal to some K value, and then for the same sample of gas at the same pressure, if we change it to a new temperature, it's going to have a new volume. But again, you divide those two, it should be equal to the same K. So the point is that Charles's law can be expressed as V1 over T1 equals V2 over T2. So V1 T1 would be like the volume and the temperature before we made some sort of change, or in one trial, or the before. And then V2 T2 is like the after. So it's like before and after. So this is a fun little experiment, basically showing Charles' law in action. So if we have a balloon filled with gas, and the gas is at room temperature because we just inflated it with our lungs, or maybe it's a little bit warmer, but then we pour some liquid nitrogen on it. So that's what's happening here. We've got a thermos with a little bit of liquid nitrogen. You could probably barely see it in the photo, but liquid nitrogen is really cold, which is why, it's actually kind of difficult to get. But the volume goes down. So notice what happened to the balloon. The balloon is definitely smaller. So all of those molecules are slowing down. They're not hitting the walls of the container, which is the balloon, as quickly. And what's happening is that the atmospheric pressure on the outside of the balloon is compressing the balloon and making it shrink down in size. So the pressure is staying 1 atmosphere, but as a result of that, the volume of the balloon is going down. So the temperature went down because of the liquid nitrogen, and the pressure is constant because it's just atmospheric pressure from whatever's in the room. And N is constant because we didn't leak any particles out of the balloon, but then we saw the volume decrease. So similar to Boyle's law, we could take Charles's law and solve for anything we wanted. So again, V1 T1 equals V2 T2. If you know 3 of those variables, you could solve for the 4th one. So this setup would be an example where they are asking for the final volume. They give you an initial volume and they give you 2 temperatures in the problem. This setup would be like they're asking what is the final temperature. They give you 2 volumes in the question, and they also give you an initial temperature. So let's do an example. So this says a 132 liter, that's pretty big, helium balloon is heated from 20 degrees C to 40 degrees C. What is the final volume assuming constant pressure? Now, one thing that's really, really important with any problem involving gases is you must convert to Kelvin. It is essential you remember that. The temperatures, 20 degrees and 40 degrees, we absolutely have to convert them to Kelvin. I guarantee you will get the wrong answer if you fail to do this. How do we convert to Kelvin? We simply add 273. So it's basically the degrees Celsius plus 273 equals Kelvin. So the reason for that, 0 degrees Celsius equals 273 degrees Kelvin, and negative 273 degrees Celsius equals 0 degrees Kelvin. We actually don't write the degree symbol for Kelvin. Kind of trying to get my eraser. I can't do it. There we go, 0 Kelvin. 0 Kelvin is known as absolute zero. That's something you've probably heard of before, but the nice thing about Kelvin temperature units is they can never be negative, which is why we like to use them for gas laws. So our temperatures in these gas law problems should never, ever be negative because you're always working in kelvins. So we're going to use 293 and 313 for T1 and T2, but we do need to figure out which one is which. So they said, what's the final volume? So that's going to be our V2, which means 132 would be the V1. And then just reading the text one more time, it says it's heated from 20 to 40. So the 40 degrees, that would be our T2. And then the 20 degrees, that would be our T1. So that's why they've got 293 on the bottom here for T1. And they've got 313 in the numerator on top for T2. And then here's our V1, the 132 liters. So kelvins cancels. And then we should get 141. And then the units, well, we had units of liters over here. So our answer is going to have units of liters. And then something that it's always good to do, good mental exercise, and also a way to check your work is just think about, did we get an answer that makes sense? So temperature and volume should be directly proportional. And what happened here? We went from 20 to 40, so the temperature increased. So we would expect the volume to also increase. Well, we went from 132 to 141, so that's good. We got a higher volume, so our answer made sense. Okay, next one, Gay-Lussac's law. So this one is about the pressure of the gas and the temperature. So pressure and temperature are also proportional. So here's a proportionality symbol. So basically, same kind of graph. As the temperature goes up, the pressure goes up. So it's also another straight line graph because they're directly proportional. So same kind of thing that we just saw with Charles's law. Instead of volume and temperature, now we've got pressure and temperature, but we could use an arbitrary proportionality constant. So the pressure divided by the temperature in one scenario or before there was some sort of change can be equal to the pressure divided by the temperature afterwards. So this is one way to write Gay-Lussac's law. And then just kind of like an illustration that's a little bit kind of common. So as the temperature of gas in a steel container increases, the pressure is going to increase. So this is one reason why we need to be really careful transporting gases. And, who's transporting gases on a regular basis? Well, every single time you go to a restaurant that serves soda or a fast food place like McDonald's or something like that, they've got these CO2 tanks inside their restaurant, and that's how they make your soda. So transporting these gas containers, they have to be really careful that they're kept at an ideal temperature, because if it heats up too much, if the temperature increases, the pressure is going to go up. And if the pressure bursts on this thing, well, now you've got a bomb. So just kind of like a real world application, basically how we transport gas in, or, gas to different restaurants. We got to keep it in these cylinders. So applying it, actually using this, same kind of thing as before. Now, this setup would be like if they asked for what is the final pressure, and they gave you two temperatures in the problem, and they gave you an initial pressure. And then the second one would be, they asked you what's the final temperature if, and then they give you two pressure values, and then they give you an initial temperature. So as an example of a problem using Gay-Lussac's law, so say a steel container of nitrous oxide at 10.4 atmospheres is cooled from 33 degrees to negative 28 degrees. What is the final pressure assuming constant volume? So notice that we have negative temperatures, but that's because the temperatures are in the wrong unit. So I've got negative 28 degrees, but that's degree C. So one thing we will have to do is convert our temperatures into Kelvin. So that's what they've done here. The negative 28, they added 273 to get 245. And then the 33, we've added 273 degrees to get 306. Now, again, the tricky part is figuring out, okay, which variable is which. Now, they did say, what is the final pressure? So that's asking for P2, let's call it P2, which means the 10.4 is P1. And then with the temperatures, so it said from 33 degrees to negative 28. So the 33 degrees sounds like it's T1. And then to negative 28 degrees, that sounds like it's afterwards, so that's our T2. So that's why they have the 306 in the denominator, and they've got the 245 in the numerator of that fraction. And then P1, the pressure beforehand, that's the 10.4 atmospheres, so we should get 8.33. And then the units, well, we've got units of atmospheres here because our initial pressure had units of atmospheres. The temperature units of Kelvin, those canceled out. So if we combine all three of these gas laws, basically we get something that's called the combined gas law. And this is a little bit different from the ideal gas law. But if we have more than one variable changing, like let's say that the pressure changes and the volume changes, they could say what happens to the temperature. We can use this thing called the combined gas law. So these are our setups. Let's say, for example, they said, what's the new volume? If the pressure changes and the temperature changes, then that is how you would set it up. If they wanted a new pressure, because the volume changed and the temperature changed, you would set it up that way. And if they're asking for the new temperature because the pressure changed and the volume changed, then that is your setup for the third one, third scenario. But let's do an example. So we've got all three variables, pressure, volume, and temperature to consider. So let's say we've got 10 liters of carbon dioxide gas, and it's at 300 Kelvin and 1 atmosphere. Then they say, what happens if the Kelvin temperature doubles and if the volume doubles? So to kind of like outline what we've got, initially, so the beforehand, this is kind of like our P1, this is our V1, this is our T1. And then volume doubling means it would go from 10 to 20, so that's our V2. And Kelvin temperature doubling, so 300 turns into 600, so that's our T2, and then we're solving for P2. So this is the setup that we want. So in that problem, they talked about the temperature changing and the volume changing, and we were given an initial pressure, and we have to solve for the final pressure. So sorting out, which variable is which, the volume changed from 10 to 20. The temperature changed from 300 to 600, and notice that they're different. So like here, V1, V2, the 1 is on top, the V2 is on the bottom. But for the temperatures, T1 is on bottom and T2 is on top. So that has to do with the fact that pressure and volume are inversely proportional, but pressure and temperature are directly proportional. But it's just something to notice. Make sure that you're putting the correct variables on the top or the bottom. And then we should get a final of 1 atmosphere. And, units, this is atmospheres because our previous pressure had units of atmospheres. So we happen to get the exact same pressure when we're done. And this makes sense because if the volume doubled, that means the pressure would go up by half. So the volume is times 2, then the pressure would be like times 1/2. And then if the temperature is times 2, then the pressure is times 2. So due to the volume, the pressure shrunk to 1/2. But due to the temperature, the pressure doubled again. So it ends up going right back where it started. So just in summary, Boyle's law, P1V1 equals P2T2. Charles' law, volume temperature, they're fractions, so V1 over T1 and V2 over T2. And Gay-Lussac's law, you have pressure and temperature, so P1 over T1 and P2 over T2. And then we can have the combined gas law. Now, I mentioned the ideal gas law. I'm not going to go into detail on this one, but it's PV equals nRT. So P is pressure, V is volume, T is temperature, N is moles of gas, and R is the gas constant. So it's a number, but depending on what units you're using for pressure, volume, and temperature, the R could actually have a different value.